back to uniform circular motion. So this is lesson 2. So lesson 2. So uniform circular motion, where uniform circular motion, UCM, occurs when an object is moving in a circular path at a constant speed. So we got to make sure that it's at a constant speed. Since velocity is constantly changing, the direction, there is going to be an acceleration. So since we have our circle, or our circumference, let's say, we're going this way at a certain speed. So our V is going to be at a certain speed. We're going to have a force, it's called the centrifugal force, which is going to be our F, pushing inwards. When we have two perpendicular forces, V and our F, our force, or the way it's going to go, is going to go into a circular motion. So it's going to go to that way. Then our velocity is going to point this way, our force is going to go inwards, and we're going to go all the way around to this side. And our velocity is going to go that way, and our force is going to go inwards. We're going to keep going around until we get into a full circle all the way back. So that's basically what we're doing over here. So when the velocity is constantly changing, there's going to be an acceleration, because the direction constantly changes. The velocity is going to go all the way around, and our force is at every single point is going to point towards the middle, regardless of which direction it's going. It's always going to be perpendicular to our velocity. So to find this instantaneous acceleration, the delta t is going to be very small. So our time here is going to be very small. It's going to be like at a 0.001 difference. We will take two instantaneous velocities, so two velocities that are almost together or almost the same, and a tangent path. So if you guys remember in math, we know that a tangent path goes through two different lines or two different points. So this is our first point, this is our second point. That's what a tangent line is. And a secant line, just for recall, is going to be one point passing through it at this point right here. So, and we will take two instantaneous velocities tangent to the path and gradually move them closer together. So until t approaches 0. So as t approaches 0, our velocity will be closer and closer together. So when v2 is really close to v1, our theta is going to be, our degree is going to approach 0. And as theta approaches 0, the direction of the delta v is towards the center of the circle. Therefore, the acceleration is always going to be towards the center of the circle. So from the rate, it's basically going to be our radius. So that's what our acceleration is going to be towards, the center of the circle. The magnitude of the centripetal force, or centripetal acceleration, can be defined by the equation A, which is centripetal, whatever it's called, this word. We're going to have our v2 squared and our r. So our r is going to be the radius of the curvature. So our r is going to be from the middle to the side. That's going to be our r. And our speed, well, we've covered speed before, which is going to be meters per second. So our centripetal acceleration is the rate at which velocity changes with respect. So this means with respect to WRT, with respect to causing circular motion. So our period, not women. Period is the time for one revolution. So rev, we can write that for short, revolution, and is measured in seconds. So one revolution just means it's going around the entire circle once. And is measured in seconds. Frequency, so our F, is the number of cycles occurring in 1 second and is measured in hertz, or S over 1. Right? So So the number of cycles, our frequency is going to be measured in how many times it goes around and around and around in over 1 second. So if it goes around 3 times over 1 second, our frequency is going to be 3 hertz. And that equation can be found as F right here, right there. All right, so occasionally speed is not given in a problem, but to find speed, we have our d over t. So for circles, our d is going to be equal to our centripetal force, or our 2 pi r, and our t is going to be equal to t, obviously. So it can also be rewritten as v 2 pi r over t. T can also be equal to 1 over f, which we see over here when it's rearranged. So our f equal to 1 over t. We times multiply this by t on both sides. Multiply this by t, so you're going to have ft equal to 1. Divide this by f, divide this by f. Our t is going to be equal to 1 over f, which we can also write in this situation. So v is going to be equal to 2 pi r f, where in the place of t, when it's over t, like this, our t over 1 is going to be equal to just f, as we see over here. So, and then our velocity, or acceleration, sorry, will be equal to v squared over r. And if we can rearrange our v squared, or remember, if we recall, our v is going to be also equal to this over here. So if we can write this as v squared will also be equal to this entire thing squared, and if we rewrite that, that would be 4, because 4 squared would be 4, well, 2 squared would be 4. Our pi, which would be pi squared. Our r, which would be r squared. And our f, which would be squared as well. All over 1 or nothing, if you guys really want to think about it like that. But remember, so this would be times r, 1 over r, because r is on the denominator. So, and if we do that, we have to cancel out this r with one of these r's. So in the end, over here, it will be 4 pi squared r f squared. That's what our equation will be like. So if we see that over here, that's what this equation would be like, as we can see right over here, right on this side. Or you can rewrite it as this, where 2 pi r over t, which will just be equal to this equation over here, we can rearrange it to fit into this part right over here. So our first question would be, a Ferris wheel has a radius of 7 meters per second and takes 0.75 minutes to do 1 revolution. So we have to determine our average speed at the bottom, the average velocity for a revolution, and our centripetal acceleration at the bottom. At the bottom will be stated over here in this part right here. So I already have it written out. So to find our a value, or to find our question a, we have to find average speed at the bottom. To find average speed, we have our v from this equation over here, which we can rewrite as this, or any of these really. So we have our v equals to d over t, so right here. Our d can be equal to 2 pi r, because we have our radius of or r, and we have our time, so we can rewrite it as 2 pi r, or 2 times pi, which is 3.141592653, times 7, all over 0.75 times 60. And if we put that into a calculator, we're going to get 0.98 meters per second rounded. We're just not going to write the thousands of decimals behind it. Now for part B, where we have to find the average velocity for a revolution. So our average velocity would be equal to 0, because when we're doing a revolution, we're going to be at a constant speed no matter what. When we're at a constant speed, our velocity will have no magnitude, therefore it will be equal to 0. Now to find c, the acceleration at the bottom. So we already know the formula for acceleration, which would be 4 pi squared r over t squared, where we have our r and we have our t. So 0.75 minutes will be 45 seconds. We just have to plug those two values into the formula to get 0.14 meters per second squared up, because at the bottom, it's going to be wanting to go up like this. That's why we write it as up. Another example over here, if we have a circle over here and we're trying to find, oh, that's not a circle. If we're trying to find our speed over here, into this section right here, this force will be always pushing up, just like how we explained it over here. When two forces are perpendicular to each other, it's always going to move in a cylindrical formation. All right, that's lesson 2 on